just go with me
Okay.
on this.
Okay.
Don't talk to me. Just go with me.
Okay.
Show me what happens if the temperature of that is absolute zero. Thank you.
It can't be.
I know, but there we go. Now show me what happens if that is lukewarm.
But
Alright, no.
yeah.
Now, show me what happens if that is very hot. Now, show me what happens if that is a negative temperature.
It has. You can't do it. This is my potential energy surface.
No, what is it really?
It's 2 chairs with a blanket over
What's
the top.
the blanket?
The blanket's the blanket the dog sleeps on when I bring the dog into the office. We have a miniature dachshund. Never, ever, 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 anybody out there ever get a miniature dachshund. They're the most disobedient dog on the face of the planet. So we are talking about negative temperatures. We really are somewhere behind the cutting edge, I guess, in terms of describing this. Brady wanted to do it at the beginning of January. I wanted to do it at the beginning of January. Brady's been away, I've been away, and unfortunately, we only get round to it now. First and most importantly, it's beautiful work. Absolutely stunning work, and we'll talk about that, all the furores about this excellent paper. Negative absolute temperature for motional degrees of freedom. But negative absolute temperatures are not a new thing. This was 1956. So this has been known about for quite some time. And in effect, every time you use a laser pointer, you're exploiting negative temperatures. Well, of course, we're not talking about just minus so many Celsius or minus Fahrenheit. We're of course talking about the absolute temperature scale. We're talking about 0 Kelvin, where if we could get there, and the third law of thermodynamics and quantum mechanics tells us we can't, if we could get there, all motion would stop. So we're talking about negative temperatures, apparently temperatures the other side of that, which you then might go, but how can you go beyond having no motion at all? That just makes no sense. It's all about how you actually define temperature. And now at this point, I don't want to disgruntle the physics undergraduates and postgraduates out there, but I'm not going to lapse into a discussion of entropy and the relationship of temperature and entropy. We could do it that way, but I'm going to do it in a slightly different way for those people who, like myself, whose head starts to hurt when you start thinking about entropy in too much detail. I'm going to talk about distributions. We know, and let's just shake these up, atoms in a box. Let's close the box so they don't go everywhere. Atoms and molecules in a box. Basically, the higher the temperature, the more they're jiggling about. That's the general idea in terms of the sort of layman's concept, or whatever you want to call it, temperature. It's more important, though, to think about the distribution of speeds, indeed the distribution of velocities. That's one of the most fundamental aspects of temperature. Or am I allowed to draw a graph? One graph, I promise. Just one graph. What we have is on this axis, we have the molecular speed. We're going to call that V. And on this axis, we have the probability of finding a molecule with a certain speed, or finding molecules within a certain range of speeds. And what we find is we get a curve that looks like that, right? Which is, as you can see, asymmetric, and it's got a peak. And if we heat the molecules up, then what we find is that that curve moves, and it also flattens. So what we find, as you might expect, if you heat it up, you get more molecules. There's a probability now, a bigger probability of finding more molecules with faster speeds. What's important is it's not a single number. You can see it's a distribution. That's really, really important. Okay. So we've got to get this concept of energy levels in our heads before we can go any further with this. So I'm knackered. I'm so unfit. Right. So to be able to explain negative temperatures, I need to move away from this type of, continuous distribution where we've got millions and billions and gazillions of different speeds here, and to think about just a simple two-level system where our atoms and molecules can have one of two energies. So they can be in what's called a low energy state or in a high energy state. All right? Very straightforward. What they generally want to do if we leave negative temperatures to one side, we're talking about positive temperatures, usual everyday things, is what happens is that the atoms and molecules want to occupy the lowest energy state. That's where you find the greatest probability of finding them. Here we've got lots and lots in the lowest energy state, lots in the high energy state. Am I allowed an equation as well? I got the graph passed.
Oh, now you're pushing it.
Just one equation.
Okay.
Right? And the way we describe this, we work out the probability of finding the atoms and molecules in those. It's a really simple equation due to Boltzmann. And the probability, P, let's call it, is proportional to, ready for this? E to the power of minus, we're going to call it delta E over KT. Right, before you balk at that. So that E stands for exponential. Or maybe I'll just, to be entirely clear, what we have is that. So this is called a Boltzmann factor. Now let's just do some of the sums. Let's plug some of the numbers in. And what we well, first of all, let me explain this. Exponential, we know what that is. Delta E is the difference. I've only got two energy levels, but it's the difference between this energy level and this, or this energy level and this one, or this one and this one. All right? K is Boltzmann's constant, and T is temperature. And what's very important here, Boltzmann's constant allows us to convert between energy and temperature. So this is energy, and this also, when you multiply Boltzmann's constant by temperature, gives you an energy. Okay? Good. Got an equation and a graph. I'm very proud. Whether it makes the final cut. So note, if you go to a very high energy level, that's e to the minus something, which means that as you go up this ladder, it gets smaller and smaller and smaller. The probabilities get smaller and smaller and smaller. Happy? If you can engineer a system whereby this happens, whereby you have very many more atoms and molecules in the higher energy level than in the lower energy, and you keep going up, so you have more molecules, then what that means is that we've got the probability of finding the atoms and molecules in a particular energy level is proportional to the exponential of minus delta E over KT. Right? So we can look at that. If we change the energy level, if we make this larger, so if we go from that level to the higher level, then this value becomes bigger, and we've got e to the minus something which is quite big, which means that the probability is quite small. However, what we can also do is we think about this in terms of negative temperatures, make that T negative, negative and negative cancel out effectively, and what we have is that. And now this is very interesting. As you go up the ladder, as you go up those various energy states, what you find is that as this delta E is growing, then this is going up. So the probability of finding the molecules up here is now greater. You see? And that's where the fundamental essence of this minus temperature comes in, because it's like you've just taken that distribution, and if you consider that what you have now is a minus temperature, what a minus temperature gives you, what a negative temperature gives you, is this change in the distribution.
It feels to me like negative temperatures don't exist. You've just found a flaw in the equation.
No, it's not a flaw in the equation. It's absolutely valid to do it this way. But the very interesting thing here is that this negative temperature is greater than any positive temperature. Right? Because if you take another object and you bring it to this negative temperature object, heat will flow, energy will flow from the negative temperature object, regardless of the temperature of the other one, regardless of the true temperature of the other one, it will flow that way. If we've got balls, let's go back to balls, the top of a hill, we'll know that up there they've got quite a large potential energy. What they really want to do, see if you just nudge them, sorry, wrong side, Brady, is do that. What we're effectively doing is you've got a negative temperature. Instead of the molecules being down there, by engineering a negative temperature, what you're doing is you're making it preferable for the molecules to stay up there. What it's equivalent to is get one of the pyramids, which is like this, and flipping it round and getting it to stand on its head. And the way you do that is why, where's the paper gone? It's why that particular paper is in Science. because it's a tour de force of experiments. What they do is they combine what's called an atom trap with an optical lattice, so they have atoms at incredibly cold temperatures, and they use interference beams of light to trap those and to modify the potential energy surface. So basically what they do is they have a potential energy surface that looks like this, an energy surface where the atoms are trapped like that, without them falling out.
You're so clumsy.
I know. Where the atoms are trapped in a little valley, and then by basically changing the experimental parameters, you want to know all about it, read the paper, what they do is they very rapidly put it like that and trap those atoms in that particular state. So what you've now done is you've moved to an energy distribution that looks like this. What I really want to get across is that they haven't gone through zero. They have not got to 0 Kelvin. That is still verboten in terms of the laws of thermodynamics and quantum mechanics. It's not what they've done. They've got a negative temperature, and you might wonder why I mentioned a laser earlier on. Well, the way a laser works is that it effectively exploits a negative temperature, because this thing, for reasons I hope are reasonably clear now, this is called a population inversion. And what happens is that electrons, which is what we're doing here, fall down from this level to this level, and they give out a photon. And but you've basically engineered a negative temperature. Again, for the pedants, and I know for 60 Symbols videos, there's quite a few of you, got to point out that there's a big difference, because this is, I guess we should have a technical disclaimer at this point. This is effectively a non-equilibrium effect. What they've done here is in essence equilibrium thermodynamics. Subtle difference.
Is a negative temperature hot or cold?
Hot. Hot in the sense that, you know, how do we determine whether something's hot or cold? Well, it's always sort of relative to something else. It's hot in the sense that if you have a normal temperature object and you bring a negative temperature object, heat will flow this way.
Just go with me on this.
Okay.
Don't talk to me, just go with me.
Okay.
Show me what happens if the temperature of that is absolute zero. Thank you.
It can't be.
I know, but there we go. Now show me what happens if that is lukewarm.
But
Alright, no.
yeah.
Now, show me what happens if that is very hot. Now, show me what happens if that is a negative temperature.
You can't do it. It's just, you can't, because what you have to have is effectively a temperature that's greater than this, the possible total amount of energy this can have. And in this particular system, you can't, it doesn't work for this system, and it doesn't work for so many systems, because what you have to do is to have a limit, to have an upper limit on the total amount of energy you can have. It's really difficult to explain, Brady, but you can, this is where the analogy breaks down. You just can't, it just doesn't work. Sorry.